How are we doing? I thought we needed a theme song. Questions while we wait for others to come in? It's Sheep by Pink Floyd. Yeah. How are we doing this morning? Questions, anybody? How are we doing with the fundamental theorem of calculus? Weekend was fine. Had a lot of work to do. I'm almost done. Questions, anybody? No, we're good? Let's wait another minute or two. We're still, no, nothing, no. Real work for the department. Nothing interesting. Morning, everyone. We haven't scheduled the midterm yet, but I want it to be the week before the break. So we'll decide when we want to think about it. Do we want it at the beginning of the week, nearer to the end? Do we want it to overlap onto the break? You can decide. The web work, I'll open up the web work when we've done enough of the material. I mean, probably by the end of the week. What topics will it cover? You're assuming you're talking about the midterm, I assume. Look, I mean, it'll cover wherever we are in the course. I mean, I don't have a set schedule of topics, so I mean, we just go with the flow. So we'll see where we get, and I'll make an announcement at some point. Questions, anybody? No? We're good with the material, I mean? Let's go back to what we were looking at last time, namely the fundamental theorem of calculus. which says that if you have a continuous function on the interval AB, and define a new function, big F, as the area underneath the graph of f of t from A to x. Right, so you understand what we're doing, right? We're defining a new function, which is the area underneath the graph. Right, so this function, big F here, is the area underneath the graph of f of t between A and x. Then this big function is continuous on the closed and bounded interval AB, differentiable on the open interval AB, and its derivative is little f. We saw that last time. In fact, we kind of proved it, right? I mean, at least giving you the flavor of the proof. Wasn't a rigorous proof, but it gives you the idea of what's happening. Let's take an example. If I define let's define big F as the area underneath the graph e to the minus t squared from 1 to x. My question to you is, what is the derivative? Well, this is exactly the situation for the fundamental theorem of calculus. And consequently, the derivative is e to the minus x squared. The integrand at x, right? The integrand with x replacing t. Exactly that. Implications of this, right? As we pointed out last time, suppose you're looking for the area underneath the graph from 2 to 3. Right? What is the area underneath the graph from 2 to 3? Well, this is the area underneath the graph from 1 to 3 minus the area underneath the graph from 1 to 2. Right? But this is big F of 3. And this is big F of 2. In other words, the implication, I'm not saying the area underneath the graph of e to the x is e to the x. What I'm saying is, if I define a function as the area underneath the graph from 1 to x, then this function is differentiable, and its derivative is this. Right? So in other words, an implication of the fundamental theorem of calculus is, in order to find the area underneath the graph from 2 to 3, all you need to do is find a function whose derivative is what you started out with, right? And evaluate it at 3, subtract evaluating at 2. So this is the connection between the area underneath the graph and the antiderivative, right? This means the antiderivative of e to the negative t squared. And consequently, in order to find the area underneath the graph, you find an antiderivative, evaluate it at the top limit, subtract, evaluating it at the bottom. Let's take a few examples. First, a few examples of the first part, and then we'll do some examples of this. Rudy's asking, was it from 1 to 3 and 2 to 3 and not 0 to 3 and 0 to 2? That would have been fine as well, but I have defined my function as the area underneath the graph from 1 to x. Had it been 0 to x, then we would have done as you had suggested. Do we have to specify the equation is continuous and differentiable from 1 to x? You do not. You do not. Consider this. Here's the question. Yeah, it's the noise was the sump pump. It goes off once in a while. What are we finding here? An excellent question. My question to you is, what is the derivative? It's a t, not a plus. T sine t here. Yeah, we're just, I mean, we introduced this last time. We're just doing a few more examples and we're moving on. We're looking for the derivative, but I mean, why are we doing this? Yes, sorry, what page was that? Page 406. We're doing a few examples because this is the most important theorem in the whole course. This is why the course is so easy, right? Because finding the area underneath the graph involves finding an antiderivative. And once you've found an antiderivative, you can always check your answer, right? Because the derivative needs to be what you started out with. So there's a way for you to always know if you're correct or not. We'll be looking for antiderivatives. And you can check by taking the derivative of your answer. If the derivative is what you started out with, you know you're right. So we're looking for the derivative. As somebody suggested, perhaps we could split it up first. We could split it up somewhere, anywhere. Let's say 0. Why do we split it? An excellent question. Because we know what the derivative is if you're going from a constant to x. Here we were going from a function of x to another function of x. So by splitting it up, and reversing this, right? Because properties of the integral. The integral from 1 minus 2x to 0 is negative of the integral from 0 to 1 minus 2x. And now you can apply the fundamental theorem of calculus to each part. This is, of course, a function of x, not just x, right? So you can think of this as u. And the derivative with respect to x by the chain rule in 140 or 139, dg dx is dg du dx. Right, so if we take the derivative of this, as we saw last time, we plug this instead of t. So we have a minus outside. We plug this instead of t. 1 minus 2x sine of 1 minus 2x times the derivative of the inside, right? dg dx is dg du dx. So the derivative of this is minus 2. And same thing here. The derivative of this, plug that in for t, times the derivative of what you plugged in. We saw that last time. If one of the numbers was negative, where would you split? It really doesn't matter. Doesn't matter. You could still split it at 0. The result would still be the same. I think you think I have an extra bracket. Thank you. Let's clean this up in a way that we can see a general pattern arising. Right? Let me rewrite this as this thing. And minus this. And understand, well, Rachel is asking if we always split at 0. Short answer, yes. But what I'm working towards is a pattern, a general pattern that works all the time so that you don't have to split. Let's understand how to go from here to there immediately. I think I do have a minus 2. Minus 2 here, right? So can we go from here to there directly? Right, what do? Plug in the top limit in for t, and then differentiate what you plugged in. That's what the chain rule tells us to do. Subtract, doing the same thing for the bottom limit. Replace the bottom limit, replace t by the bottom limit times the derivative of what you plugged in. This is the general approach. When do you need to multiply by the derivative? Always. Always. If your function, right, I mean, let's repeat with the example we just did. If we're looking for the derivative of this, plug in the top limit in for t, so you get e to the negative x squared, times the derivative of what you plugged in. Derivative of x is 1. Subtract, doing the same thing for the bottom limit. E to the negative 1 squared times the derivative of what you plugged in. But derivative of 1 is 0. And you get exactly the answer we had before. You can split it up anywhere. At 0, at 2, it doesn't matter. It doesn't matter because the derivative of a constant is 0. And is asking why change from t to x. That's what the fundamental theorem of calculus tells us to do. Let's take another example. Same question. We are asking what is the derivative? Somebody's asking, we just do antiderivatives and now we're differentiating integrals. The thing is, before the fundamental theorem of calculus, we did not understand that an integral was really an antiderivative. It's the fundamental theorem of calculus that tells us that. Because this was just notation for the area underneath the graph from 1 to x. It's through the fundamental theorem of calculus that we understand the connection between antiderivatives and the area. So we're looking for the derivative here, the derivative of this function. What do? Plug in the top limit in for t. So arctan of 2x times the derivative of what you plugged in. Subtract, doing the same for the bottom limit. Subtract, doing the same for the bottom limit. Derivative of what you plugged in, 1 over 2 of x. You can split it at 3, you can split it anywhere. I'm suggesting you don't need to split. We've understood how that works. Plug in the top limit, and then differentiate what you plugged in. Subtract, doing the same for the bottom limit. So big F is the integral of little f, exactly that. How are we doing here? Questions? Is everybody comfortable with the fundamental theorem of calculus? Absolutely. You can always split it anywhere as long as your function is differentiable. As long as your function is continuous, right? You can split it anywhere and it makes no difference. User is saying, so the answer is the antiderivative? No, this is not the antiderivative. This is the derivative of this function. You don't have to show steps. You can always use this process. Is it possible to simplify the expression? Yeah, it probably is. You can put everything over a common denominator. I would just leave it as this. Why? Seelan is asking, why isn't the answer just arctan of x? Well, it would have been arctan of x if this had gone from a constant to x. That's what the fundamental theorem of calculus would have told us. but it's not that. It's different, right? It's going from root x to 2x. So you would expect the answer to be different as well. Yeah, we are applying the power rule here to find the derivative of root x, and we'll get a 1 over 2 root x. It's not equal to the function, it's equal to the derivative. F prime. This is your function. This was the original function. Now we have its derivative. All right. And it's this fundamental theorem of calculus that explains how to find the area underneath the graph. In order to find the area, all you need to do is find an antiderivative. What's the point of finding the derivative? It's actually not the derivative that's important, but the understanding that the area underneath the graph now corresponds to antiderivatives. And so let's take an example. In what cases does this not work? It always works. Fundamental theorem of calculus, as long as the integrand is continuous, you're good to go. I mean, the problem is in high school, you know, they tell you to find the antiderivative and then that's it. But they don't explain why the antiderivative corresponds to the area underneath the graph, or vice versa. Consider this. We're looking for the area underneath the graph of this from 0 to 4. Fundamental theorem of calculus. Bahar is asking, what's the difference between antiderivative and integral? Well, the fundamental theorem of calculus tells us there's no difference. That's the beauty of the antiderivative. That's the beauty of the fundamental theorem of calculus. So fundamental theorem of calculus tells us in order to evaluate the area underneath the graph, we need to find an antiderivative. So what function has derivative x squared? Well, I mean, you know from calculus 1 that you just finished doing, you can work backwards. You know that 1/3 x cubed, you know that the derivative of 1/3 x cubed is x squared. 3 comes down, canceling the 1/3, and you're left with x squared. And what function has derivative 4x? Well, again, you can work backwards. And 2x squared has derivative 4x. Let me introduce some notation here. This bar from 0 to 4 means you plug in the top limit and then you subtract plugging in the bottom, exactly what the fundamental theorem of calculus tells us to do, right? I've rubbed it off, but it was f of 3 minus f of 2. So big F of 4 minus big F of 0, what do we get? If you plug 4 in, you get 64 over 3 minus 32. Subtract, plugging in 0, but when x is 0, everything is 0. And there you go. Does it matter that the derivative of 22 equals 0? Where's the 22 come from there? Can we do 37? Number 37, give it to me, Sean. So what is that? This is going to be negative 32 over 3. Stephen is asking, this is F prime. It is not F prime, it's big F. It's your big F. Sean is asking, so 37. The integral from, Sean, I've lost you. Two plus x squared over square root of x. And did we have limits for this? Sean? So somebody's asking, when should we find the derivative and when should we find the antiderivative? Well, that's the thing, right? I mean, here, you're given a function big F and you're asked specifically to find F prime. That's the question, so you answer the question. Here, they have not defined big F, they just want the area underneath the graph. So here you understand through the fundamental theorem of calculus that you need to find an antiderivative. We found an antiderivative, plugged in the limits, we're good to go. Why didn't we just replace with 4 and 0 like the other examples? We did replace with 4 and 0, but here, I mean, these are two different questions, right? Here I'm asking for the derivative. Here I'm asking for the antiderivative. Sean is saying from 1 to 4. There we go. So let's try that. We're looking for an antiderivative. And it's important that you don't start making up your own rules for antiderivatives. Right here you have a quotient. The antiderivative of quotient is not the quotient of the antiderivatives. We should rewrite this in a way that's easy for us to find the antiderivative. You don't remember using intervals for integrals, so how do we make these work? Well, the fundamental theorem of calculus, as we showed before, right, with the f of 3 minus f of 2, in order to evaluate an integral, you find the antiderivative, you plug in the top limit, subtract, right, plug in the top, in for x, you get this, subtract, plugging in the bottom limit. This is what the fundamental theorem of calculus tells us to do. Let's do this example. But before we do it, we need to rewrite this in a way that we can deal with. And let's split it up into two things. 2 over root x plus x squared over root x. We haven't done anything yet. We're just manipulating the integrand. Somebody's asking about what about the derivative of 22. The question wasn't asking for the derivative, so there's no need to do it. But let's talk about the derivative. Look at this function, right? This is what I was saying. that you can always check your answer. What's the derivative of this? The derivative of this is, right, I mean, you bring the 3 down, they cancel, so you get an x squared minus 4x, exactly the function you started out with. So you know that you're right. You can always check your answer. There's a question here. The reason we find antiderivative here is to find the area, while previously we found the derivative to find the function whose area is given by the interval. Essentially, yes. I mean, I think it's perhaps not worded as well as it should have been, but you essentially have the idea there, yes. All right, there are too many questions. I can't keep up. Let's just do a few questions. Here's what I propose. Let's do a few questions, and I'm sure everything will clear up. And if not, we can answer them in a few minutes. So we need to rewrite this in a way that we can manage this 1 over root x is really x to the negative 1/2. And here, x squared over root x, this is really x to the 3 over 2. Now you'll remember at the end of 139 or 140, we were looking at antiderivatives. And we had actually noticed right, since the derivative of x to the n since you know how to find the derivative of x to the n is n x to the n minus 1, right? You bring the power down and you subtract 1 from the power. The antiderivative is going to be the opposite, right? You're going to add 1 to the power. But you know the derivative of x to the n plus 1 is n plus 1 x to the n. You don't want the n plus 1, so we're going to get rid of it by dividing. And this is true as long as n is not negative 1, as long as the denominator is not 0. And in the case of negative 1, what function has derivative over x? Well, you know that to be ln x. So here, the antiderivative of x to the negative 1/2 is x to the negative 1/2 plus 1 over negative 1/2 plus 1. And the antiderivative of x to the 3 over 2 is x to the 3 over 2 plus 1 over 3 over 2 plus 1. Let me rewrite that up there so that we can reference it. The antiderivative of x to the n is 1 over n plus 1, x to the n plus 1, or n not equal to negative 1. And the antiderivative of 1 over x is ln. It's actually absolute value of x. 37, this was the question in 37. That's all they gave us. What does that represent? It represents the area underneath this function between 1 and 4. Kenza is asking, why didn't we divide by n instead of n plus 1? Or isn't it divided by n instead of n plus 1? No. Right? What's the derivative of this? This is a constant derivative of x to the n plus 1. You bring the n plus 1 down, it cancels with that, and you're left with x to the n. Exactly what you want. Let's finish that up. Negative 1/2 plus 1. This is 1/2, and it's in the bottom, so I'll flip it, and I'll get a 4 x to the 1/2. And over there, that's going to be 2 over 5 x to the 5 over 2. Between 1 and 4. And again, let's verify. Before we plug in the limits, let's make sure that this is correct. What's the derivative of this? The derivative of this, the 1/2 comes down, canceling with the 4, giving you 2. 2x to the negative 1/2. 2x to the negative 1/2. The derivative of this, the 5 over 2 comes down, canceling completely with the 2 over 5, giving you a 1. X to the 5 over 2 minus 1, which is 3 over 2. So the derivative of this is x to the 3 over 2. There it is. The derivative of this is exactly what you started out with. You know it's right. Plug in the top limit. Subtract, plugging in the bottom. Square root of 4 is 2. 2 times 4 is 8. Square root of 4 is 2. 2 to the 5 is 32, 64. Minus 4 plus 2 over 5. So 4, 20 plus 66, 86. 86 over 5. There it is. Is it? Is it wrong? We made a mistake? Why did we minus? Oh, yeah, probably just a probably just a typo there. So let's take 4 away. What do we have? 86. So we 82. 82 over 5. Thank you. Absolutely. Sorry about that. Don't let the V fool you, right? I mean, it's always the same thing. We're looking for an antiderivative. Whether it's X or V, it's just a dummy variable anyways. What function has derivative 1? You know what function. X, or in this case, v. What function has derivative 8v cubed? It's a 7, correct, a 7. What function has derivative 8v cubed? Two v to the 4. And what function has derivative 16v to the 7? 2v to the 8. Jonathan is still not sure where we're trying to find the antiderivative of the integral. Well, it's not the antiderivative of the integral, because the integral and the antiderivative are synonymous. It's the antiderivative of the integrand. This is known as the integrand. And that's what the fundamental theorem of calculus tells us. In order to evaluate the integral, you find an antiderivative of the integrand. You plug in the top limit into the antiderivative, subtract, plugging in the bottom limit. Right? And again, you can verify that this is the right answer by taking the derivative. Derivative of v is 1. Derivative of this, you bring the 4 down, you get 8v cubed. Derivative of this, bring the 8 down, you get 16v to the 7. You know it's right. You know it's right. Plug in the top limit. So 1 minus 2 plus 2. Subtract, plug in the bottom limit. 0 minus 0 plus 0. Answer is 1. Paul is asking, what was the purpose of finding the derivative? To understand that, right? I mean, we had a function given like this, and we found the derivative, and we showed that it was little f, which means that the original function was the antiderivative, right? If the derivative is this, then this function is the antiderivative of the little function. And that's what allows us to use the antiderivative to find the area underneath the graph. Right? Because before the fundamental theorem of calculus, these were two separate entities. The antiderivative and the area underneath the graph. Is there a relationship between the two? That's what the fundamental theorem of calculus answers. I have office hours, noon to 2, Tuesday, Thursday. They're posted on my courses. Yeah, so when you find an antiderivative, you find an expression equal to the integral. Absolutely. And when you plug in the numbers, you get the area. That's exactly right. Sealant, if you go to the content section and you scroll down, there is a place for office hours, and all the office hours are listed there and where it's hosted. Tutorials are starting this week, absolutely. Fresca is starting this week as well. I'll have I'll post a schedule on my courses. It actually starts today at 2:30. Webworks are not, there's nothing up yet, but I'll post one at the end of the week. Antiderivative, why is it called the antiderivative of the integrand and not integral? They're interchangeable terms. So it is called that, absolutely. Consider this. Consider this, again, tempting as it may be, don't make up your own rules for antiderivatives. Nolan is asking, what's the purpose of the idea of f of b minus f of a? That's to find the area underneath the graph. The area underneath the graph from a to b is the antiderivative at b minus the antiderivative at a. Right, Rachel, there's a web work 0, which is not for marks. But I'll post the first real web work today. So again, right, the point is, don't make up your own rules for antiderivatives. Here we have the antiderivative of a product. It is not the product of the antiderivatives. We have to rewrite this in a way that we're able to work with. And the simple thing to do is to expand this. This is 4 root t minus t to the 3 over 2. Let's take it a step further and rewrite this as 4t to the 1/2 minus t to the 3 over 2. These are now just powers of t or powers of x, and you can use this rule. Work out the antiderivative. Right, let's do the 4 outside. Antiderivative of t to the 1/2. According to this, this is t to the 3 over 2 over 3 over 2. Antiderivative of t to the 3 over 2, so minus, is t to the 5 over 2 over 5 over 2. Clean this up. You're dividing by a fraction, we'll multiply by the reciprocal. 8 over 3, t to the 3 over 2, minus 2 over 5, t to the 5 over 2. And again, at this stage, you can verify that this is the right answer, right? If you differentiate, you should get back what you started out with. So the derivative, the 3's cancel, 8 over 2 is 4, 4t to the 1/2, looking good, minus the derivative of this, you bring the 5 over 2 down, cancels completely, and you get t to the 3 over 2, perfect. So that's why you need to be strong with the derivative, because you can now check your answer. We've checked, we know it's right, we can plug in, plug 4. Square root of 4 is 2. 2 cubed is 8. 8 times 8 is 64. Square root of 4 is 2. 2 to the 5 is 32. 64. 5 minus 3 is 2. 128 over 15. I should have mentioned when you plug 0 in, you get 0 for both, of course. How are we doing? right? People saw immediately that the answer was 0. There's nothing to do here. Very nice. Right? This is one of the properties of integrals, right? The integral from a to a is 0. Very nice. There it is. You know what to do. We're looking for a function whose derivative is equal to this. We're looking for an antiderivative. You have experience with the derivative. We can work backwards. What function has derivative sine x? Right? You know the derivative of cosine x is negative sine x. So negative cos x will have derivative sine x. Thank you. And similarly, what is the antiderivative of e to the x? Well, you know the derivative of e to the x is e to the x. And there it is. Again, you can verify that this is correct. The derivative of this is exactly what you started out with. These are all on page 406. Absolutely. Plug in the top. Minus 2 cos 3 minus e cubed. Subtract, plugging in the bottom. Minus 2 cosine 0 minus e to the 0. Cosine of 0 is 1. E to the 0 is 1. So this is minus 2 minus 1, which is minus 3. There it is. Well, I mean, that begs the question, how are we doing? All right. Well, I want to ask if there are questions now, but all right. Is there one more? Right, I mean, if you forget the 4 that you can pull out as one of the properties, you recognize this. Do you know a function which has this as the derivative? You know exactly which function I'm talking about. What function has this as its derivative? Absolutely, it is arc sine. Thank you. Arc sine. So this is going to be arc sine of 1 over root 2 minus arc sine of 1/2. I don't know why I have brackets now, but there it is. Arc sine of 1 over root 2, you know what it is. That is pi over 4. Arc sine of 1/2. Arc sine of 1/2. Pi over 6. So that's 2 pi over 12. 2 pi over 24, pi over 12. Answer pi over 30. So following these examples, I think we now understand the relationship between an integral and the antiderivative, right? In order to evaluate this integral, you find an antiderivative and you plug in the limits. So in practicing finding antiderivatives, we don't always need to plug in the limits. And so we now introduce the notation for an antiderivative. Right, so we will now go back to the notation we were using in Cal 1, and this will represent the antiderivative of f of x, right? So, it's really the same thing, but without any limits. Here we're looking for the general antiderivative. Sometimes referred to as an integral. So to distinguish between an integral with bounds and an integral without bounds, we sometimes refer to this as a definite integral, right, where we have limits. So definite integral. Versus an indefinite. So indefinite integral and antiderivative are synonymous. And there it is. Now, we have, right, so, I was already using this notation here, the antiderivative of x to the n is 1 over n plus 1, x to the n plus 1. We had already seen this in, what did I say was synonymous? The term indefinite integral and the antiderivative, they mean the same thing. Right, we had seen in Cal 1 this nice formula. And as you know, the derivative of a constant is 0. So, if you differentiate this, you get back to that. But so is the derivative of 703, right? In other words, if you add any constant, the derivative is still the same. So a general antiderivative will have an arbitrary constant at the end, because you know the derivative of a constant is 0. And by the mean value theorem in Cal 1, we saw that if two functions have the same derivative, they had to differ by at most a constant. So this idea of antiderivatives makes complete sense modulo the arbitrary constant. The indefinite is really because there are no limits here, as opposed to a definite integral, which has limits. So let's take a few examples. Right, so here there are no limits, so we're not viewing this as an area underneath the graph, but really just an antiderivative. The question is, what is the general antiderivative of this function? You know what it is. First, I mean, maybe we want to rewrite this as 5 plus 2 x to the 1/2, if you will. And you can use this formula. What function has a derivative of 5? You know what it is. 5x. What function has derivative to x to the 1/2? Right, leave the 2 aside. Antiderivative of x to the 1/2. That's x to the 1/2 plus 1 over 1/2 plus 1. Throw in your arbitrary constant at the end, and there you have it. You're dividing by a fraction here. Let's clean that up a bit. 5x plus 4 over 3 x to the 3 over 2 plus your arbitrary constant. And again, the beauty of this is that you can verify that this is correct. Take the derivative of that. You need to get back what you started out with. We can do this in our heads, right? Derivative of 5x is 5. Derivative of this, if you bring the 3 over 2 down, the 3's cancel. You get a 4 over 2, which is 2 x to the 1/2. 2 x to the 1/2. Derivative of a constant is 0. Beautiful. So why do we need to add plus c for indefinite integrals? Only need to add plus c for indefinite integrals and not definite integrals, right? It's certainly a valid question. And let me postpone the answer for a few minutes. You'll see exactly why. But it's certainly a good question. Why not plus c when you're doing definite integrals? You'll see what we'll answer that in a moment. But before we do, let's do a few more examples of the indefinite integral. What function has derivative u to the 6? Right? It's 1 over 7 u to the 7. Same thing here. 2 over 6 u to the 6. 1 over 4 u to the 4. 2 over 7 u. Throw in your arbitrary constant at the end. Indeed, it does cancel out. We'll see it. You're right. You're right that it cancels out. We'll see it. Let's do 1 or 2 more examples of indefinite, and we'll come back to the definite integral, and we'll convince ourselves. Right? here's our proposed answer. Again, you can verify that this is correct. Derivative, if you take the derivative of this, you should get back to that. Let's do it. When you take the derivative, 7 comes down, canceling, and you get u to the 6. 6 comes down, canceling the 6, you get a 2 u to the 5. 4 comes down, canceling, and you get a u cubed. Derivative of 2 over 7u is just 2 over 7. Derivative of constant is 0. Consider this. Again, we don't want to make up our own rules. Let's expand, simplifying the integrand. Does the indefinite integral have the same properties in terms of operations we can do with it? Absolutely. Absolutely. What properties are you referring to? The linearity, right? The antiderivative of a sum is the sum of the antiderivatives, because you know that to be true for the derivative itself. And the antiderivative of a constant times a function, you can pull the constant out and find an antiderivative for the function. That's also true because it's true for the derivative, right? And the antiderivative is just the opposite operation. So if we expand, this is secant squared plus secant tan. Do we know of a function whose derivative is secant squared? Or what is the antiderivative of secant squared? Thank you, Maddie. You know a function whose derivative is secant squared. That function is tangent. The derivative of tangent is secant squared. What function has derivative secant? X tan x. You know the derivative of secant is secant tan. The derivative of secant is secant tan. Add in your arbitrary constant, and you're done. Kenza is asking how it works with factors and how we can split it. I don't know what you mean by factors. If you just mean a constant, then yes. C can be anything. C can be any constant, absolutely. Let's take an example. Let me change these to x's. Doesn't matter, right? I mean, these are just dummy variables anyways. Whether it's x or it's t, it's the same thing. And we'll answer the question, right? Because now we're back to a definite integral. Stephen is asking, in your work, you have to explain or justify your work by saying by the reverse power rule, right? I mean, these are going to be trivial. Nobody's going to ask you to justify this. This is trivial. immediate. Of course, so let me stop it there, and let's say this reverse thing, it's new to you now. We're getting used to it, but you'll see in the weeks to come that it'll be second nature and nobody's going to question that. Right, so Kenzo is asking if we factor out the multiplicative constants that are inside the integrand. Absolutely. You can do that with definite and indefinite integrals because you know it's true with the derivative, right? The derivative of a constant times a function, you can leave the constant outside and just differentiate the function. So it must be true for the inverse operation as well. It must be true for the integral. Consider this. Our first step is going to be to expand. And we're going to use this example to ask the question, right? Because again, it is a definite integral now. In the indefinite integral, you have this plus a constant. Is that going to play a role here? Well, we start by finding an antiderivative. Right? So, I mean, you do exactly the same thing as if it was an indefinite integral. What function has derivative x? You do not need to state continuous and differentiable before doing anything. At least not now. At least not now. There will come a time when you're going to have to be careful, but not right now. What function has derivative x? 1/2 x squared. What function has derivative x squared? Right, I mean, I think you know what it is. So 1/3 x cubed. Let's throw in the arbitrary constant just to see what happens. And this is between -1 and 1. So how do we evaluate this? You plug in the top limit, you know what to do. Plug the top limit into c, you just get c. Subtract, plugging in the bottom limit. 1/2 -1 squared -1/3 -1 cubed plus c again, right? I mean, there's no place to plug in the 1 and -1. It's a constant. So it's always c. And now when you open up the brackets, you see what happens, right? You have a plus c here, and then you have a minus c. They always cancel out. As was predicted earlier, the c's always cancel out. So there's never a need to throw in an arbitrary constant there. This cancels out with that, and we get a -2/3. Does everybody see the c canceling out? And does everybody see that it's always going to happen this way when you have a definite integral? So there's never a need for an arbitrary constant when you're doing a definite integral. When it's an indefinite, yes. So Asma, when you're doing a definite integral, you never have to bother with the plus c. All right. Definite integral again. You know the difference. What function has derivative 4 over 1 plus x squared? You can take the 4 out if you prefer. And what function has derivative 1 over 1 plus x squared? You know exactly. What function has derivative 1 over 1 plus x squared? You tell me. Still haven't seen the answer yet. What is the antiderivative? Arctan, thank you. Arctan x. So this is 4 arctan of 1 minus 4 arctan of 0. Arctan of 1, you know what it is. That's pi over 4. Arctan of 0 is 0. Answer is pi. There it is. How are we doing? Questions here? Next time, we're going to ask the question, what about finding antiderivatives of more complicated functions? Can't we use ln in this situation? Tempting, right? It's tempting to ask the question, should this be 4 ln of 1 plus x squared? And let's verify by taking the derivative. What is the derivative of this? If we take the derivative of ln is 1 over, so it's 1 over 1 plus x squared. But you know that the chain rule kicks in, and we have to differentiate the top, we have to differentiate the inside, and then we get a 2x, which is problematic. Even if you take a 1/2 out, it's the x that's a big problem. The x is a big problem. There's nothing you can do here. So this is not, and you know, I mean, some people are going to want to cancel out the x by, you know, maybe making everything over a 2x. Tempting again. But now, when you take the derivative of this, it's now a quotient. So quotient rule applies, and you know it's going to be far from this. Yeah. So next time we're going to ask the question, what about more difficult integrals? Integrals that we cannot just read off. How do we find integrals of things like this? So we're going to look at our first technique of integration. Right, so in Cal 2, right, I mean, in Cal 1 you had rules for derivatives. If it's a product, you have to apply product rule. If it's a quotient, you have to apply quotient rule, and so on. Here we have techniques of integration. There are no rules, but there are ideas. Techniques, things you can do to find antiderivatives. So we'll look at our first technique, which will answer how to find the antiderivative of such a function. We'll see that. We'll see that on Thursday. Exactly that, as Kinza suggests. The technique is known as a U substitution, but we'll see that then, along with other things as well. So thank you all for coming, and I will see you on Thursday. No more problems. That's it. I mean, quite often we go past the time, so now, I mean, it's exactly the time for us to end. We'll do so right now. Thank you all for coming, folks, and I will see you on Thursday. You guys have a good one.